Start recording. Oh, Mohammed here. Good.
Yeah.
So, yeah. So today we have Prathyush. Is that how do I pronounce your name?
Yeah, that's it. Pratyush. Yeah.
Prathyush. Good. So I mean, his first time he's met us. So I thought it would be. Yeah, maybe what we should do is start by introducing ourselves to him, so he knows who his audience is, and then he can, and then I can introduce him a little bit to you, and then you can take it away. How does that sound? So I'm Michael Lawler, and I'm a theoretical physicist working in strongly correlated electron systems. I've been very interested in quantum computing related things, but I'm interested in whether we can use, in the area, for example, of quantum simulation, or the areas where it could be applied to help us understand strongly correlated electron systems. And so part of our interest is, from that angle, is to understand exciting things that are going on in strongly correlated electron systems, so that we can participate in that. Let's see. My background is in frustrated magnetism and in non-Fermi liquids. I did my PhD thesis on pneumatic quantum critical points. Anyway, so I guess that's rough picture of who I am, and maybe maybe that will give you a sense of who else is here. They all work with me.
I guess so. Yeah.
But I don't know. So anybody else want to introduce yourself?
Sure.
All right.
Hi, Pratyush. My name is Gaurav. So I'm a fifth-year PhD student with Michael.
Mm-hmm.
So I've mostly been working on using quantum computing to simulate fermions and other strongly correlated systems.
Mm-hmm.
And my interest right now is
so just wait a minute.
Yeah, my interest right now is in I guess trying to understand condensed matter systems from the perspective of quantum information, especially trying to understand entanglement.
Mm-hmm.
And also using dynamics in order to gain an understanding of these systems by the help of quantum computers and simulators.
Okay.
And you're a Cornell graduate student.
Yes,
you're at Cornell. Okay.
Yeah. Which year are you in? I forgot.
This is fifth year.
Fifth year. Okay.
Yeah.
This is my fifth year.
Very advanced graduate student. Great.
Yeah.
Let's see. Anybody else want to go?
I can also introduce myself.
Yeah, you can.
Should I? Can you hear me?
Yeah, I can hear you. Hi.
Okay, hi. Yeah, my name is Christopher Owen. I'm a grad student as well. I am at Binghamton University, though, not at Cornell. Although I have been to there a few times, and it's a nice school. This is my 6th year, I think, as a grad student. Time flies by, so it's always hard to keep track of that.
Yeah, right. Okay.
Yeah, it's been a while.
Good for me to know.
Yeah, I've been in Dr. Lalu's group most of that time. I am interested in physical systems, but I'm interested in trying to model them in a simplistic way. So I try to take a simplistic approach to what I do. I also like to hike a lot.
Nice.
Yeah. That's about it.
All right. So, we don't. Not everybody has to introduce themselves. I just thought I'd give you a sense of.
Yeah.
Actually, there's We have a lot of undergrads in the group, but they're not here today. I don't know why. I'm gonna make
Okay.
sure they know more about this event, so hopefully they'll be here next time. But so you just have mostly graduate students, so that maybe that's nice. So as I understand it, Pratyush is a graduate student at University of Maryland, working with Shankar Das Sarma. Is that right?
Yeah.
And I was just checking out your archive list there, and I saw that Pratyush has 4 papers, 3 of them from this year. Is that right?
Yeah. So it was. I think few of them. There's going to be 2 more coming up from the last year, which is called Held Up.
I see. Very nice. So he seems to be producing lots of papers. That's wonderful. And the papers seem to be focused on superconductivity, Moire materials.
Yeah.
I don't know. Maybe you can tell us a little more as you present.
Yeah. So currently, right now, I'm working on Moire systems in general, I guess. So I also have a collaborator. So I was in Europe last year. I was working there as for my bachelor thesis at the University of Luxembourg, and so that's where I also met Matthias at the University of Innsbruck and started collaborating with him also. And it's been primarily on Moire systems, superconductivity, and analyzing the role of fluctuations in them, which I will talk more about in my talk.
Okay.
And here I'm also additionally doing Hartree-Fock calculations on different Moire systems based on ab initio band structure kind of way.
Okay.
We do that. And and I also have a side interest, I guess, from my previous position in higher order topological insulators.
Okay.
And like Marina modes. So that, so I've been working on that.
For people who don't know what a higher order topological insulator is,
Mm-hmm.
it is a material you've probably heard of topological insulators, which have a surface state. But then it was discovered that actually you could have a situation where the surface is also gapped like an insulator, but like the edge is gapless. And then, of course, you could go even another step higher than that, and maybe the edge is gapless, but the corners of the system are the edge is gapped, but the corners are gapless. So there's this notion of higher order topological materials.
Yeah. So if you're coming to APS, my talk will be on that. You can feel free to attend. So
all right. Well, so why don't you take it away? And
perfect. I just need to figure out how do I share my screen here.
Okay. Yeah. So there's a little like a TV-like button at the bottom beside your.
At the bottom on the side.
Beside your
room.
Yeah.
I found it. Yeah. Screen share. Allow. And see my screen?
Yep.
Okay. Good. And okay, it's right here. Nice.
Yeah. Good.
All right. So, hey everyone. I'll be talking about my work here. I guess you can find an archive, which, basically tries to understand a different kind of superconducting state from a phenomenological perspective in Moire systems. All right. And I call it conspiracy among fluctuations because this is a superconductivity primarily mediated by the fluctuations themselves, and it's purely that among the fluctuations, which are like bosonic fields. And then through the coupling of the bosonic fields in the electron sees the superconducting state in a sense. All right. So I'm not going to explain what it means. And here, this density of state is basically the key result that we have, where we find that the superconducting state we find has a nodal-like kind of structure in the electronic spectral function, right? And so this is a very broad overview. And now I'm going to go more into detail about what I did right from the beginning.
Can I ask a quick question? So the red curve there doesn't look like a node to me. It looks like
I'm going to come up to that. So basically, turns out we find a phase transition to a fully gapped state.
Oh, okay.
Yeah. So that's also one more thing. So that's all. It's all in this one picture. So it shows both nodal-like and gap-like. And this is also seen in experiments where they find a transition from a V-shaped kind of thing to a U-shaped density of states in Moire systems.
Okay.
Yeah. And override the small picture, it's basically shows what the superconducting state is. It turns out to be made out of 4 fermionic particles, 2 electrons, 3 electrons, and 1 hole together. And so, yeah, so this is the global broad overview, and I'm going to start my talk with that. So feel free to interrupt me and ask me any questions that you like. Yeah, so that's fine, you can make that informal. All right, so starting off with graphene. Graphene, if you're not familiar with it, you can let me know, but it's basically a hexagonal lattice system with a normal tight binding structure with nearest neighbor, things like that. And turns out the key interesting part about graphene is that you have low energy Dirac nodes at 2 points in momentum space. They are called the valleys. You have K and K dash points in momentum space, where the band structure goes linearly in mod K as you move away from, and more as you move away from the K and K prime point, and they are called the valleys. Okay, and so graphene effectively can be described by the low energy degrees of freedom, the spin degree of freedom and the valley degree of freedom. Valley is also in a sense like an isospin because it's you have 2 of them, and you can describe them in terms of in a similar approach as you can describe spin using symmetries. Now, what you do is you take 2 layers of graphene, slightly twist them, and put them on top of each other. And so what you get is a resulting Moire structure. Now you have sites where they are all perfectly overlapped, and then there are sites where they are not overlapped. The stacking changes from like AA to AB to BA, and then you get a periodicity over a larger length scale, which is the Moire length scale. And turns out if you do a band
Is that a relaxed lattice picture?
Sorry?
Is that a relaxed lattice picture? Because like there's 2 different situations, right? There's you twist, but you keep all the atoms exactly where they are mathematically. Or there's the experimental situation where you twist and they relax.
Yeah, there is no relaxation taken into account here.
No relaxation, because
no relaxation.
Quite, I think it looks pretty stunning. I guess with the relaxation, the AB regions become larger, right, and the AA regions become smaller or something like that.
I'm not very familiar with how the relaxation is taken into account here. I don't know what that would look like.
I see.
In terms of that, I'm not familiar with that.
As I understand, the AB region, if you have a lot of if it's mostly AB, then it's sort of more chiral, right? Because you're always going from an A site to a B site. So you've got this closer to this chiral limit.
Yes.
But, okay, right.
So that, but I think in some of the ab initio parameters, I guess, so the Moire systems, I guess, can be described by some ab initio parameters, I guess, TDBG, and for example, I think if you look at twisted TMDs, they do take into account the lattice relaxation when they do the ab initio calculations, using density functional theory or something like that, and then you get an effective low energy model that we can use. So in cases, lattice the relaxation can be taken into account, but I don't know about this specific case of in graphene. I do not know how they do it, but but then that will turn out to be in our calculations. The low energy model of graphene turns out to be not very important. We don't use a low energy exact model of graphene.
Okay.
We use a phenomenological band structure. The key role, as I'll come to say, is what we need are the fluctuations. So the way that fluctuation comes in is, if you look at the band structure of the twisted graphene system, it becomes literally very flat, over momentum space. And so it's very non-dispersive. That means if you look at it in a tight binding sense, your T and T dash are a bit small. And so what that would mean is that your interactions now play a much important role. Because what happens, you need for strong correlating effects, you need your interactions to be large relative to the kinetic energy. So in this case, when you have flat bands, the kinetic energies are quite small. And so you get strong interactions. And then because strong interactions, now we can get some very nice, interesting phases of matter. And these phases of matters are characterized by broken symmetries. You can have, for example, transition symmetry breaking. You can get charge density waves, and then you can have various magnetizations. So the spin you can order, and you can get magnetization. You can also have the symmetry breaking with respect to the valleys. Different valleys can coexist, can be correlated with each other, and also various different combinations of them. You can have all different kinds of things that happen together. And also superconductivity. which is my main interest in this talk. Now here are like some few phase diagrams. It looks like you see some dome-shaped superconductor. I took this from some various papers, which had some twist angle. You can see superconductivity, metal, and then nearby there's like a Mott phase, basically a Mott insulator, and that is characterized by some other kind of symmetry breaking over there. And so you see the superconducting phase, the phase boundary is oftentimes nearby other phases also. So, and what happens is the fluctuations of these other phases will be important within the superconducting regime also. There will be a competition between the two of them, something like that. For example, so here are some few cases. This is twisted double bilayer graphene. So this is one of the experiments that I'm currently looking at, where what they had is the TDBG. It's very hard to find superconductivity in there, but then they put it on top of WSE2, which has kind of spin orbit coupling. That means valley, I guess in a sense, it's like one valley has spin up and the other valley has spin down. And it has a valley antiferromagnetic order that way. Sorry, was that a question?
No question.
Yeah, sorry.
No,
yeah. And so it's a very small, weak thing. But then nearby, IF2 is basically intervalley. It's an isospin flavor polarized region over here. And then similarly, if you look at rhombohedral trilayer graphene, there's no twist in this, but then you can see there's a small layer of superconductivity right next to a huge insulating phase, which has some other symmetry broken parameter. And then similarly over here also, you have some superconductivity right next to some other polarized phases in terms of over valley or spin.
How did they measure? How did they make these nice plots?
So over here, I guess this is basically I do not know experimentally how they do it, but rather what they measured here is, in these two cases, are the resistivity, and they're showing the color plot of the resistivity, the longitudinal resistivity.
Oh, I see.
Over here, they don't look at the resistivity, but rather look at the Hall conductivity, Hall density, the difference of the Hall density with respect to the actual density. And what this tells you is kind of how much a degeneracy is broken. So you have spin and valleys, that's like some degeneracy of 4. But now, when you have some kind of a symmetry breaking that occurs in like the valley or spin space, this lifts the degeneracy of some of the band, making them either completely empty or completely unoccupied. And in that case, the Hall density, that measures how much of your band actually contributes in the charge carrying process, that will not be equal to the actual density. The Hall density will be different from the actual density. And that will tell you, like, in a sense, what's the degree of degeneracy that's broken. Now, crucially, to note, one thing to note is that it's very hard to know what the exact symmetry breaking that occurs is within these isospin. They usually just call it isospin flow polarized phases. Took me a while to understand what they meant. But yeah, but then there are some other phases. The difference with the Hall density is how they figure that out. Yeah. So do you have any questions, anyone? All right, yeah. So the key point I'm trying to make here is that over here, the fluctuations of the correlating phases will definitely play an important role, especially in cases like these, where you have superconductivity, a small region of superconductivity occurring next to like a huge symmetry broken state over there. So now there is this idea that because the fluctuations are important, the interactions from these fluctuations can give rise to unconventional pairing. Now, what am I showing here? NQ is in a sense a spin vector. You can describe spin fluctuations by some kind of a bosonic field that orders. And then it's some kind of an interaction that gives rise to it. It's an attractive interaction over the spin space. So this prefers like a ferromagnetic ordering, so to minimize the energy. So this would be like an effective interaction that mediates symmetry breaking, normal symmetry breaking in terms of spin ordering or value ordering, something like that. But now what you can have over here, so what you can do here is that this kind of an interaction, you can decompose them into different channels of the superconducting pairing. and like in a BCS kind of way. So a good reference for this, I guess, is Sidney Coleman's book does this very nicely. And so when you decompose it, turns out in the superconducting channels, you can get singlet pairing or triplet pairing within that comes out that arises from these kinds of fluctuating interactions, and that can give rise to superconductivity. Yeah, I wanted to write it down here, but also I forgot to put that in. So that's generally one of the ideas that these papers on the right have followed. Fluctuations, integrate out those fluctuations, get the interacting term, decompose the interactions into the superconducting pairing channels, see which one dominates. So that's one line of thought that is very common to analyze these kinds of situations in a very phenomenological manner.
So they're doing it's a mean field theory, I suppose, right?
Yes, it's a mean field theory.
And they're looking for the leading instability in mean field theory.
Yes.
And you mentioned at the beginning of this slide that this NQ, I guess if you decompose in the particle hole channel,
Yeah.
then you get normal conventional order, not superconducting. And then you decompose in the particle-particle channel, then
Exactly.
you get superconductivity. And so did these sources, did they try to see which one wins, superconductivity or normal? Like if both of those are possible out of the same interaction, was that, or does they just assume they are going to check whether what the
So in this case, I'm trying to recall. I think. Okay. I think one. I don't think either of them checked for the TC. I will have to double check it. I don't recall seeing a comparison of TC from the fluctuations for the ordering of the fluctuations themselves. So that I do not recall seeing that, no.
Okay.
But I think these are the primary references that I've been following over here. They're relatively recent. But
So quick question.
Usually they do a comparison of TC from various different superconducting channels. But this is also this nice paper by Levitov's group where they classified all possible interactions, and then that can give rise to and then looked at the leading fluctuating instability for these. They looked at all possible symmetry breaking orders in the particle hole channel. I mean, it doesn't break U1 symmetry.
I see.
And looked at the leading instability for those fluctuations, and then looked at the interactions resulting from that, and then decomposed that in the whole channel, and again looked at the leading superconducting instability in that. So like various ways you can people have played this game here.
Yeah.
So it's all very interesting, like the different ways people come up with to analyze the system. Yeah.
So quick question.
I think this would also have to do. Usually, when you have these spin fluctuations at finite temperatures, when you take into account the fluctuations, I don't think it order. So that's one of the people. Okay, I mean, in both cases, you do mean field, so it's kind of not fair to compare it. Yeah. No. So coming back to that, I think I don't recall looking at ordering in the fluctuations itself.
Can I ask a question?
So is that fine?
Can you hear me?
Yes.
Yeah. Actually, I remember this one other paper with just a and looks at both and finds that they actually look at the transition to an intervalley valley ordering state, and then looks at the fluctuation nearby the valley ordering state. So there are actually papers that does both. Yeah.
I see.
So I don't know if I've put that reference here, but I can send that over. Okay.
Have access.
Yeah.
Gaurav, you have.
Yeah, I have a question. You can hear me, right?
Sorry, what?
Can you hear me? Doesn't seem like he can hear me.
Yeah.
Oh, I see. That's the issue. Now it makes sense.
Yeah.
I can't hear you.
There's
Yeah, we can hear Gaurav, but yeah.
Wait, can you hear me?
we can hear you. No problem.
Oh, okay.
But there's it's possible here in Gathertown that you can somebody could be muted. One of the people could be muted on your side.
on my side.
I don't know how that could have been the case, but it sounds like Gaurav is muted.
So should I unmute him or wait? Who should I unmute?
Yeah, maybe is there something on his?
On mine?
Can you say something again, Gaurav?
Can you hear me, Pratyush?
I can
have
hear
a
you.
question
Yeah.
for you.
Oh yeah.
Okay,
Sure. Yeah.
great.
Perfect.
So I'm assuming like NQ here is the charge density at point Q.
Right. It's not a charge density. It could be like a spin density wave also at momentum Q. Because it's a fluctuating wave. So it can be charge density. That means there's nothing in the spin space or something like that. But it can also have spin ordering, or it can also have valley ordering that combines together. That is overlapped on top of this charge density wave.
I mean, there could be, right?
That could be.
But NQ is just like, C dagger Q, CQ kind of operator.
Yeah, but then there can be something in between that couples different spins and values. So so the idea is, I wrote this in a very generic way because there are very, very different ways in which they can do this. And the way you can classify all these different kinds of things is by symmetry. Because the original model will have some valley symmetry, spin, rotation symmetry. And you look at representations of those symmetry and classify them. So yeah, it will be
I see.
like projected density onto the low energy bands. Is that right?
No. So I think that's different. So people do that. Yeah. So that's how. So that you usually do if you're looking at just the Coulomb interaction.
Okay.
So that's one thing I do. You start off with the Coulomb interaction, project the Coulomb interaction onto these. So one thing what people do is if you look at this band here, they look at this low energy band and then project the Coulomb interactions onto these bands. And in that case, your interactions would be just a charge density wave over this, or projected onto these low energy bands. But then if you're starting off from the some fluctuations, you assume a priori that there are some bosonic fields that is already present with some kind of a bosonic propagator. And that describes these kinds of these fluctuating parameters. And in that case, you kind of assume a priori what you're ordering. You say that, okay, I have an intervalley ordering. I will assume with spin, I will put this in.
I see. So just to make it clear, right? So so NQ, N minus Q here is like interaction between right, like interaction between like different channels, right? Spin and valley.
Yeah, it could
like
be
all degrees
yeah.
of freedom, right?
Yes.
But when you do your mean field calculation, you choose to break a symmetry in like one specific channel and then like carry out the calculation.
Yeah. Now keep in mind this interaction here doesn't break any symmetry. The symmetry is broken when NQ orders for either like Q equal to 0 or maybe some finite Q. But that's why, because they are fluctuating. These are fluctuating fields. Their expectation value is 0. But they still play a role in terms of the interaction system. The fluctuations can give rise to pattern. That's the main.
I see, but like how do you take into account fluctuation in your like mean field calculations?
Yes, I will. So that we just plug it in by hand. That I will come to that. I will come to that later on when I'm discussing the model. So in that case, I think it will be clear on how we take into account the fluctuations. But basically, we plug that in by hand. It's very phenomenological how to do this here. But
I see.
Yeah.
Okay.
May I ask a quick question too?
Sure. Yeah.
Maybe this is quite elementary, but I was wondering if as you said, the stability of the superconductivity modes due to field fluctuations is a matter. It's not something. Can you explain it more? How we can make sure if they are they going to be somehow managed in order to be stable?
So how they're stable? So it could be stability. You mean the stability? How do you look at the stability of the superconducting phases? Yeah, ordered phases. So one thing is mean field theory. So I guess in that case we don't take into account the stability against fluctuations. But what people have also done is you can do a large N theory which I think that is a reference on by Prina Narag's group recently, where basically you solve the interactions taking into account Gaussian fluctuations, up to Gaussian fluctuations and not more than that. So that's one way you can analyze the stability of the state. But in that case, what happens is that most of your vector order cases, like for example, triplet superconductivity and all that, they order at T equal to at zero temperature, but at finite temperature they get disordered due to Wagner theorem. When I heard of it, so in mean field it'll show a transition, but at finite temperatures, if they do this large n calculation and take into account fluctuations, then it disappears. It goes to zero. So many times, yeah, it's important to consider the stability of the superconducting phase also in fluctuations, and this large n kind of way theory is one way to do that.
I see.
Yeah, I can send over that references. So I guess that Nature paper and Narang's paper, yeah, these two. I keep a note of this.
Sounds
Yeah,
good.
so that is one paper which does this, and it's a nice paper. Yeah. So any questions?
Thank you.
All right, so I will move on. Now, this was fluctuation mediated pairing. I'm going to talk about fluctuation mediated superconductivity, which sounds very similar, but I will say why I've titled it a bit differently. So this, I guess, is a crux of the idea that we have, Matthias and I. Basically, you have here some kind of a magnetization vector that does not order, its expectation value is 0. dq expectation value is also 0. And what is dq? That's the vector that describes our triplet superconductivity. So triplet superconductivity is kind of, I will come to what the exact formula, or how it looks like, but it's rather a spin state between C and C. And it's a bosonic vector field. But the dot product of them, the inner product, it condenses. This is a scalar value, dq dot nq. The dot product of two different vectors. And that condenses, which we call the vestigial phase, and breaks U1 symmetry. So dq, because its superconductivity transforms by some gauge with respect to like the U1 gauge field. But because these two are vectors, they cannot individually condense at finite temperature, but their dot product, a number, can condense. This is a very high level thing, a high level explanation of what I'm doing. And then the idea is this gives you superconductivity, and through their coupling to the electrons also get a superconducting response. And the thing is, how do you write down the theory for that? Well, you can write down a generic Landau-Ginzburg theory that preserves the symmetries, So we have different symmetry. You have U1 symmetry, all the electrons that transform or something. You have spin rotation symmetry, you have C2C symmetry, and you have time reversal symmetry. And all these N and D that transform according to those. But like, it's kind of like not important right now, but the field D dot N. You just look at the symmetry and you look at how you write down a symmetry invariant Landau-Ginzburg and see at what regimes you get this kind of a phase. All right, so now coming to the model, you have the coupling of the bosonic fields to the electrons. So you have the spin polarization, and now I'll talk about exactly what these NQ and DQ are, what they correspond to. So NQ corresponds to basically the expectation value of spin times tau z. Tau z is in the valley space. So that means the spin vector is antiferromagnetic in valley space. So the spin points in one direction at valley up, and then in the opposite direction at the other valley, the down valley, for example. I'm calling up and down. And the expectation value of that is described by NQ. This here is the triplet superconducting field that's given by S vector times ISY tau y. Because of this tau y factor, remember that the superconductivity is between pairing at different values, The valley, plus valley pairs up with the other valley. And because of this, you can get a momentum independent gap function when D condenses, So that usually in triplet superconductors, you need your momentum dependence to be inversion antisymmetric. So it cannot be momentum independent so that it satisfies the fermionic anti-commutation relations. But because now you have different pairing between different values, your dq can have a finite expectation value at q equal to 0. And there will be a constant thing. So this is the triplet superconductivity. At t equal to 0, it gives you a full gap.
Sorry,
And now
what is little less?
a little less.
Yeah, the in
Here?
front of the D, the other S.
Oh, so this is the S vector. So this is an inner product between S vector times D vector. And this is basically Sx, Sy, Sz.
Spin vector.
The spin vector, yeah.
Oh, I see.
So that kind of describes the ordering because triplets you need, yeah. So it's basically the spin vector, and that this whole S vector times Isy tau y.
I think of that as Pauli matrices.
Yeah, it's polymatrices. It's exactly polymatrices within spin space.
Right.
And even here also it's the same thing, So this is the general spin ordering, but now because of tau z, it's in opposite direction on the two values. Is that fine?
Yeah,
Questions?
for me at least.
So let me know if you have any questions. And now we can also write down a general potential for the D and N fields. We have various different terms. What we care about, so you can get like a phase diagram, At t equal to 0, you have N and D that don't order. You get like some phase diagram at different parameters are broken. But now,
So could you tell like what NQ here is? I'm just trying to understand this this action that you wrote.
yeah.
So you say that like NQ is spin polarization.
Yes. In different values taken in together.
So what does it look like?
It's a bosonic field, So think of it like a mean field expectation value. When NQ gets a non-zero, so a non-zero, it takes a non-zero vector value, then it breaks spin rotation symmetry, and then the C dagger S tau Z C K C gets a finite expectation value. So NQ is basically the expectation value of this operator C dagger S tau Z C K.
Can you explain why you chose this particular? So you mentioned there's a whole bunch of different orderings you could have chosen. So why choose this one?
Yeah. So this is basically because so that is. Let me see if I have that reference here. So I will talk about that reference later on. So basically, there are some microwave experiments that are done recently which shows that this kind of valley antiferromagnetism plays an important. These kinds of fluctuations have been detected in Moire systems, and in general, I think spin fluctuations are important from based just by looking at the vicinity of the phase diagram. So that is, I will discuss those experimental references. One of them was here actually. Here, this TDBG thing. In one of these cases, it turns out to be spin polarized. So that's why the S vector comes in, and the spin fluctuations are important. And the specific form, so once you decide spin fluctuations, you either get either valley ferromagnetism or a valley antiferromagnetism. And then we chose antiferromagnetism just for concreteness, and also I think that was a reference, which is that in a paper actually, where they found that this plays an important role. This specific form plays an important role. But you can do the same analysis for, instead of tau z, tau 0 also.
Okay.
Yeah. So, but the spin fluctuation part is certainly the most important one, because that's what determines your magnetic charge ordered phase, that spin ordered phase in the vicinity, like that does occur quite frequently by these superconducting cases. Yeah.
So is there a dot product between like?
Yes. Yeah. It's like S dot N and S dot D.
S dot N. Okay. So S is the spin operator, right?
Yeah. Yes. Sx, Sy, Sz, that whole vector.
And then you have tau Z as well.
Yes.
Right. So
that couples between C dagger and C. So C here is the electron operator that contains C spin up, valley up, C spin up, valley down, C spin down, valley up. It's like a 4-dimensional thing that has both spin and valley space included together. And the S and tau act over the C. And N vector is a normal bosonic complex field. or n is a real field and D is a complex field.
So N is a bosonic field.
Yeah.
I see.
And D is a bosonic.
N is just like 3 real numbers, right? N of Q. Or
Yeah.
the complex
Yes.
is something
Exactly.
like that.
3 real numbers. Yeah.
S. And then the S is really the operator that's connecting to,
Yes.
to this the C the 4 fermion vector.
Yeah. Exactly. The 4-component fermion matrix.
Those C's are 4-component vector.
Vectors. Yeah.
S is acting in one of the 2 tensor product sectors.
Yeah.
Tau is where it's
Exactly.
operating in the other one. And the N is just. The reason I know this is because that's how the D is organized too. It uses the same notation.
Yeah. So that's the idea here. That's exactly yeah. So S and tau are 2 fermions. NQ is just the 3. It's a bosonic field, complex or real numbers. And that we have just plugged in this coupling by hand. And then we write down.
So coupling between. So it describes the coupling between these electrons
and these boson
the bosonic fluctuation.
Yes.
Okay. So right. So why is this fluctuation bosonic? Right, like this N is still a fluctuation in, you said that like N describes the fluctuation in various degrees of freedom of the electrons.
Yes. So it's a, I guess in the Parthenay kind of way. So C dagger C is a boson, is because it's a 2 fermionic thing. This whole field together acts in a way like a bosonic field. If you want to describe its ordering, it will be coupled to what it couples to will be a bosonic field.
I see. Okay.
Because it will be like a product of 2 Grassmann variables, I guess. But I mean, like together they form like they have like they commute with each other. A pair of 2 fermions. So I guess mathematically that's how. Yeah.
Gaurav, you're taking Subir's class this semester. I have a feeling by the end of the semester you'll be an expert on these things. No worries.
Yeah, but the thing is, like, I've already, I already took this course with Una.
I see.
So this is just like a review for me.
Yeah. Okay. Anyways, please proceed.
Yeah. And so the idea is once you have these bosonic fluctuating fields, you try analyzing them separately. Okay? And so you look at the potential of the way they interact with each other. You have like a lot of different terms. All right, and that's fine. What you look at is this D dot N squared term. What this can give you is when C1 is smaller than 0, then this will encourage D dot N to get a finite expectation value. So think about it. So at t equal to 0, N is not, N can order and D can individually order. And then we can have these composite order parameters also. That is D dot D, D dot N, and D dagger times D dot N. These are different symmetry, the breaking order parameters, scalar order parameters that you can construct and that can condense at finite temperature. Now, what happens is at t greater than 0.
Sorry, one more question. So why is there no D dot D term?
Sorry? What is
your SV? Is that basically a Landau-Ginzburg?
Yes, we write the Landau-Ginzburg theory.
So where's the quadratic? Isn't there a quadratic in D terms?
The quadratic in D will that comes from the So I haven't written that down yet. That comes up. That will come up now. That's gonna come up. So the quadratic. Let me just come here. So that's gonna come up here. This is what the quadratic in D term looks like.
Okay. So there's a quadratic in D term.
Yeah, that's a quadratic in D term also. But the reason is over here it's basically this interaction that plays the main role. Over here, we are trying to see in what case can we get D dot N, and so we can have a small phase diagram at finite temperature based on mean field theory itself, where one of these order parameters condense or not. So we have phase A, where you have like phi dd is not 0, or phi dn is not 0, or phi ddn which is not 0. And so when C1 is smaller than 0, that is this part, B1, B2 phase, then we get phi dn not equal to 0. We also get phi dd not equal to 0. That's fine. So these two together. Now, what we have is, if dd or dn condenses, then U1 symmetry is broken, exactly what we mentioned before. And that gives us superconductivity. And through this coupling SC with the fermions also get a superconducting response. And so now I will describe that, the main theory of that. Now,
And you got this figure, this phase diagram, by just minimizing this potential, right?
Exactly.
I see.
Is minimize the classical potential. So that's why I just wrote the potential over here. We just try minimizing this V here, and then see what the phase diagram is.
And did you derive, did you also try to derive these coefficients, the B1, B2?
So the derivation of this, I guess, so in these kinds of spin fermions model, it's kind of circular, because you see the D and N are intrinsically fermions themselves. They come out from the fermions. And so in some sense, that's like a double counting that goes on, but rather the way we derive them is by integrating out the fermions and then expanding it in D and N. And I guess phenomenologically, the way you can think about it is that when you integrate out high energy fermionic modes, then you also get these fluctuating N and D modes that come in. And within this mean field theory where you integrate out the fermions, then indeed we can find that C1 is smaller than 0.
Okay.
Yeah.
I wanted to know that. Yeah. So
Yeah.
you were able to derive these coefficients.
Yes.
And do indeed find that you can go to the.
Yeah. C1, we are in this phase, yes. So that is something we had to check just to claim that. So
that's
also a parallel
standard calculation, though, right? From like Gorkov or somebody, right?
Yeah, it's a standard calculation. It's very simple. So this is like half a page in our appendix of the paper.
Yeah.
So it's very small. So it's just integrate out and calculate what C1 is, and we can derive this coefficient. But in our case, it's C1 that's important, because we want that to be negative. So that's and then you can do that. But also you might not note that it's kind of a circular way to derive these coefficients, because you're in a sense double counting the electrons.
Yeah, are you sure about that? Because like the usual way, you do a mean field decoupling of your 4 fermion terms.
Right. Yes, exactly.
And then you have a complex order parameter. That's just a real number. And then you integrate out the fermions, and you get a potential for that order parameter.
Yes. But now what I'm going to do next is, and what people do next, and like even in the fluctuating case, once you integrate out the fluctuation and get the interactions, you're gonna consider the electrons again that interact with the fluctuations, right?
Oh.
But then the fluctuations come from the electrons themselves. So that's the trick. But like the logic people use is that these fluctuations come from integrating out not these electronic modes, but rather the high energy electronic modes.
Yeah. So
where there's a cutoff in post.
I think I understand what you're trying to say.
Yeah. So keep that in mind in the back of like all these calculations. And people this is the I guess accepted calculation, but this is I guess kind of I'm trying to understand it myself better, and I think it's a generic problem. Another place where
it's a phenomenological approach to condensed matter, right?
Yeah.
So that's what it is.
So this is also the same problem that pops up if you want to look at, for example, competing phases in a mean field kind of description. You have a single interaction, but then how do you decompose them in different channels in a consistent manner?
Yeah.
So that's something. This is a point I wanted to shortly mention. But and I guess is that fine for all?
Fine for me.
Yeah, cool. Well, let me know if you have any questions. Yeah. And now, what one thing I want to point out: what is this D dot N term represents? This is basically the expression of that is basically means that you have C dagger C, and then C dagger term together. So it's 3 C daggers and 1 C. It's 3 electrons and 1 hole that condense together. So it's like a 4 particle term, that 4 particle state over here that interacts together. So it's not a normal BCS kind of superconductor. But keep in mind, phi dn is you only break U1 symmetry, and so in that way, this is basically symmetry equivalent to a BCS superconductor. There's nothing special. There's no spin symmetry being broken over here. Just keep that in mind. This is like a normal BCS. In symmetry-wise, it's indistinguishable from a BCS state.
That I doubt that somehow.
Symmetry-wise, because you break U1 symmetry already, right? If you have phi dn non equal to 0. I'm talking about just symmetry wise, but it turns out to have not non-BCS properties. Like the properties of the state is vastly different.
But it should also have a different symmetry, like if n is spin, so there shouldn't there be also should be doing something in spin, right?
No, so that's the thing. It's an inner product, So D transforms as as a vector. N is also a spin vector, and so D dot n is a simple scalar. So it's spin rotation invariant.
Huh.
So that's the main here. So only you break only U1 symmetry from this.
Okay. This is you're going to tell us it's about this 4-particle condensing.
Yeah.
So they're together forming some kind of a
Composite order parameter.
composite, yeah.
Yeah.
Some symmetric object, but they break U1. So it it definitely breaks U1, but nothing else seems to be.
Nothing else. Yeah.
Okay. Wow.
That's
pretty fancy.
Yeah. So just U1 symmetry breaks, but it has like.
Have people studied these 4-part? People must have studied 4-part things. So that you're going to borrow from their work, or?
No. So what other works have looked at is they looked at transitions of, for example, D squared. They look at 4A superconducting states. D squared, D star square, and all that, which I guess, and they also, I think they break time reversal, I think, and probably not. I don't think so. I don't recall. No, I don't think it does not break. Yeah, that's fine. No. So the D squared things, but they look at basically the mean field theory, and look at when you have this condensation and these kinds of. So these are the what we call like the vestigial order parameters, and many of these have been studied before. What we are specifically looking at is the spectral function of these things, which to our knowledge has not been looked at before. Yeah.
And are you also going to discuss how it couples to electromagnetic fields? Like how
Yes.
the magnetic response the same as the superconductors?
Yes.
That kind of thing.
Yeah. So that we did that calculation. Yeah.
Okay, good.
That's what we're going to discuss it. But that's going to be just a short thing. So yeah, I'll come to that. That's like in the very end.
You only have 6 minutes though, so
I have 6 minutes. Okay. I'll probably zoom through this a bit then.
Yeah,
Okay.
maybe you want to give us a sort of higher level.
Oh shit! I lost track of time. Yeah.
Higher level at this point.
Okay. Sorry. Yeah. So this is D dot n. And so okay. So I will talk about the theory for the phase. So the phase diagram, not phase diagram. The action total looks like this. You have the electrons. You have the propagators for the bosonic fields. You have the coupling of the bosonic fields to the electron, and you have the condensate from the bosonic fields. This is what gives the superconductivity, phi dn. And then what you do is you integrate out the electrons, and you get effective interactions. Sorry, integrate out the bosons, and then you get the effective interaction for the electrons. It will be SQ dot minus SQ DQ dot DQ, and you get all possible things. SQ DQ are basically the states. They are the fermionic states for the spin ordering and also the superconducting triplet ordering.
Okay.
And now the first part is basically normal in the sense that it does not break U1 symmetry. But then this S2 term, that is SQ dot DQ dagger and DQ dot SQ, this breaks U1 symmetry. And so that is what gives you the superconducting response. And then what you do is you calculate within perturbation theory the self energy of the electrons from these interactions. And basically those self energy will have terms like you have an electron that goes in, gets scattered by an N, and then scattered by a D, and then comes back. And so this is this is in the particle channel, and gives you the off diagonal contribution to the fermions. So this would go for as if your Green's function, you just shift to Nabu space where the pairing is between plus valley and a hole in the opposite valley. And through that, what we get is that gamma y is the off-diagonal part in Nambu space, that couples C dagger to C dagger or CC. And turns out this is somewhat proportional to epsilon in a sense, the self-energy contribution from that term. And so what do the density of states look like? Over here in A, this is for very small epsilon. the self-energy contribution goes in a sense linearly with respect to epsilon for very small epsilon. So what happens is this basically renormalizes your effective band mass. And because of that, you get a suppression of the states, of the number of states available at the Fermi level. Because your density of states is proportional to like the band mass, if you look at a parabolic band structure. So what will it look like? So we have, this is, for example, the density of states. Density of states as a function of energy. This is for like a very small phi naught. And then when we do the calculation perturbatively, we find that increase phi naught, it becomes like a V-shaped. Because of the suppression at omega equal to 0, it becomes a V-shaped superconductor. And then it becomes very large. It becomes U-like also. If it becomes like a U-shaped superconductor also.
So the blue curve is basically 0 finite. Like you can't see that it's there, right? In this.
Yeah.
Then so then you start so finite is the how ordered
it's the vestigial order.
This d dot n order parameter is.
Exactly. Yeah.
And okay, and then you just plotted this density of states as a function of the strength of that order as just a parameter you tune.
Exactly. Yeah. And now also here I've taken into contribution the fluctuations that come in from the normal terms also, which is why you see that the density of state goes up large. So I will discuss that contribution also. The normal contribution, how they affect the self-energy. Now we see partial suppression, and then you can show that you have an analytical value for this suppression at omega equal to 0.
And the density of states plots on the left. Sorry, I didn't.
These are not density of states. These are, I should be clear, these are spectral functions.
Yeah, those are spectral functions.
Yeah.
Nice. Electron spectral function, which
electron spectral functions. Yes.
Like the RPES spectral function.
Yeah.
Okay.
Yeah.
I see.
It's just that. So this is basically the green is the blue is a free case, so it goes linearly. I mean, the peak go linearly as epsilon because they occur at epsilon. But then when you take into account sigma 3, the spectral functions get shifted away. The peak gets shifted away. Yeah. And then for large epsilon, so the bottom B is for very large epsilon, so that's like factor of 10 power minus 2, this is 10 power minus 1. And then it kind of like goes back, the contribution dies out for large energies. Yeah. And so these things with these are actually observed in experiments where people have found nodal-like states. And in many cases, like in this same paper, they found there's a transition from a nodal-like state to a U-shape density of states. And also in twisted bilayer graphene. And so this is kind of like the possible alternative explanation for this data. Though we have not done a ab initio band structure calculation.
Alternative to what?
To an actual nodal. So usually a V-shaped superconducting state. Sorry?
A V state would be a normal nodal superconductor with pairing.
Yes, exactly. Yeah.
The U shape would be a normal S wave, let's say.
Yes.
Superconductor. But it could be a U shape could also be any other. It just depends on the use.
Yeah.
Fermi surface.
Yes. But in our case, we have a momentum independent pairing function that breaks only U1 symmetry, and it's a scalar. And it's like, but then you get both these regimes occurring within the same model, depending on parameters.
Okay.
It starts off from like a V shape and then becomes U shaped. Exactly like you see, it starts off from a V shape and becomes a U type shape.
So then I guess because we're kind of running out of time, but the key question then is: so what is the experimental signature you want to see? So you're consistent with this these experiments, but you have a very different proposal for explaining them.
Yeah.
You need an experiment that would distinguish your order parameter from a normal superconductor. That'd be a smoking gun kind of experiment.
I am not sure what a smoking gun signature for our state would be. This is something,
I see.
I would need to think about that. So I do not know what a smoking gun signature would be for our state.
I see.
Yeah.
Yeah, that's like I don't know about Nobel Prize winning, but it's a good thing. If your theory is correct, that'd be amazing, right?
Yeah.
A 4-particle, it would be wild to see if this is correct.
Yeah.
So there's a smoking gun signature of this. And I guess another thing is we can go back to Mohammed's question about stability.
Yes.
Right. So if you have 4 particles, why not, why are they, keeping 4 particles bound? That seems like a tricky confinement kind of problem, right? Usually 4 particles could separate into 2.
In a case, we were thinking about like what would be the interaction that gives rise to such a state, and that would be like a 4-body interaction itself. That would be like C dagger, C dagger, C dagger, C, and then C, 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 C,
right.
kind of thing. And it's kind of wild to think about that.
Yeah. So the confinement problem is a good problem, theoretical, right? Like going beyond your mean field level here.
Exactly.
Trying to understand the confinement problem. That would be a good theoretical problem, I guess. But maybe if you had your signature,
that would be nice. Yeah, that's actually a very interesting question.
If experiment found it, then you might go, okay, we really better understand the theory.
Yeah. So that's an interesting question. Yeah, I'll think about that, and if I get something, I'll let you know. Yeah. Thanks.
All right.
Now, okay, I will skip past the effect of normal interactions a bit, but key conclusion is that the spin fluctuation push the states away from the Fermi level, while the superconducting interactions bring the things together. That's the reason for why it happens. But like together, if you look at both the spin fluctuation and superconducting fluctuation, it just renormalizes your density of states at the Fermi level, effectively. So that's just the effect of the normal interactions, but they're not very important, so I'll skip through them. What we do is we do a mean field theory for the vestigial pairing. That is, we write down an effective Hamiltonian at ignoring the the temporal effects. We just take omega equal to 0, and then we write down an effective Hamiltonian for the interaction. Start by integrating the formula. This is what it looks like, and then do a mean field decoupling of the spectrum. What we find is that we get a mean field solution for the renormalized energy and also the pairing. And what we have is 2 regimes. One where this beta k, which is this coefficient here, C times NF. C is basically phi by Rn Rd minus phi naught square. I don't know, But you have 2 different regimes where like this coefficient is smaller than 1. And in that case, it's perturbative. What we get is the spectrum is basically linear in epsilon. The gap is also linear in epsilon. And that leads to your renormalization of the bandmass. In the other regime, as you decrease the temperature below C by 4, then you get like a hard gap that opens up. So this is, for example, these are basically the formulas for epsilon and delta and E. E is like your total spectrum here. But rather, what happens is you have this epsilon, renormalized epsilon as a function of original epsilon. The slope here increases until it goes to infinity, and then the gap opens up to make things consistent. It comes up, hits it here, and then in the other side, it's like a non-perturbative regime here. And then this is what your spectral function looks like. It starts off flat, becomes V-shaped, and then a gap opens up. It becomes a hard gap that opens up. So we see that's the second transition that occurs within this mean field model, where it goes from V-shaped, and the states are completely suppressed, and then it becomes BCS kind of U-shaped. Yeah.
I see.
Yeah.
So that's also kind of striking from an experimental perspective. You just lower the temperature. If you see the V, go to a case where you see that V shape, and now cool further.
They do. Over here.
That's temperature?
Sorry, no, this is not temperature. Okay, probably I should look at with respect to temperature. That would be a different thing to look at.
What if you really need to see?
Sure. So I guess, the thing is, your temperature changes with respect to C, which depends on the other parameters you vary. So effectively, I guess, for a fixed, I guess the question would be for this U-shaped kind of thing. If you now increase the temperature, will it change into a V?
That's another way.
But I think. But I think this. But the thing is, the key idea is we have captured both the transitions in a model in a sense, But then, but then again, the question is now, how do these parameters come in? Since we have put them in by hand, what do they correspond in terms of the experiments? And then a calculation we did is that we tried showing this is actually a superconductor, and the thing is looked at is the off-diagonal long-range order. which is basically the fermionic two-particle wave function. And we can show that an existence of long diagonal off-range order implies the Meissner effect of like expelling magnetic fields. And so you can also construct the wave function, which is oscillating and decaying, also modulated by the Fermi wavelength. We've done that only numerically, like the theory calculation turned out to be very hard. For the bosonic fields also, we can do a we can do a off-diagonal long-range order calculation, and it turns out to depend on the some Bessel function, the zeroth Bessel function. Yeah, it's like some integral mathematical games that. Yeah, and then it matches very well in numerical research. So it's completely exponentially decaying, no oscillations. And then we also look at stable under fluctuations, in the sense that what we did is we wrote down Landau-Ginzburg theory for phi by integrating out the bosonic fields. And then we get the parameters R phi, V square phi. And we get that R phi is negative, which is a good thing for low t. And then this would mean that the phi gets a non-zero expectation value. So that's it, yeah. Oh, sorry. Oh, shit. I don't know what happened here. My slideshow seems to be messed up a bit. Sorry, just 1 minute.
You're going to clean it up?
Yeah, I'm going to clean it up real quick. I didn't notice. Yeah. Yes.
All right.
So the conclusion. So what we get is the bosonic fields condensed via a vestigial order parameter. And then you get, that's basically from this interactions, you get phi dn. Dn is not zero. And then you couple that with respect to the electrons. And then the effective interactions that you get by integrating out the bosonic fields is perturbatively connected to the Fermi sea. That means this operator has a non-zero expectation value, which is why it ends up being linear in epsilon and omega. And that gives you a separation of states at Fermi level, and what makes it nodal like. And we see a continuous transition to a hard gap. So that's it. Yeah, that's my talk. I hope I made it. I'm 10 minutes late, I guess.
10 minutes late, though. That's still fine. Yeah, we asked a lot of questions. So, yeah, thank you. I don't know.
Thank you. Yeah, any questions from anyone?
Yeah. Any more questions? I guess the answer is no.
Sure. So you can always reach out to me if you have any questions.
Yeah, so, right. So I was, this talk was recorded, right?
Mm-hmm.
And there are several people who are not even here today. And so they might watch the recording and then would like to ask questions that way. And so I guess I was thinking, I guess there's two places we could ask questions. There's a chat thing in YouTube where this is streamed.
A chat thing in YouTube, okay.
Or we could invite you to a Slack channel in our Slack page. So
Sure.
as a guest. So I'll think of one of those, whichever seems best.
Yeah.
And I'll probably send you an email so that
All right.
people could ask. Then you're going to give us a few references.
Yeah.
So that'd be nice too. So.
Sure.
All right.
Yeah.
Yep.
That sounds good.
Well, thank you very much for joining us today, and I wish you all the
Thanks
best.
for having me. Yeah, it's nice to meet you all.
Thank you.
See ya. All right. Yeah.
Thank you so much.
By the way, if you're coming to March, I guess we can meet up there. Just let me know.
Oh yeah.
Drop me an email. Yes. So I'll see you in 2 weeks.
Right.
See ya. Bye-bye.
Bye.
Bye-bye.